In the next subsection, we'll look at the Lempel-Welch compression algorithm. It's part of a family of compression algorithms named after Lempel and Sif. Many of them in some form or another are in all the compression methods that are used in practice, in particular the zip formats. They all build on some form of this. And the Lempel-Welch format is probably the cleanest to explain and implement, so we'll focus on that. But you'll get the idea of the others from the same algorithm. To explain the concept, I picked something that needs no words really, but it illustrates perfectly well what Lempel-Sif compression is like. So stare at this for a moment, and I'll have a Slido question for you. I'll show you in a second. To decode the second to last line, I think. Yeah, the second to last line of the poem is what I'll ask you on Slido. So here's that thing again, but I'll leave it in the big picture so you can see it better. And this question basically is my experiment also, whether this is self-explanatory enough or whether it does need a few words to make sense. So just this part is what you're supposed to produce. Not sure if adding more lines to this picture is a good idea. Maybe. Maybe more like that. Okay, I see many right answers, so maybe we don't have to wait for everyone. What the goal here is to illustrate if you have a text that is somewhat repetitive, like this poem, you can often specify what comes next if you're trying to read what comes next here by saying, I've actually seen this before. I'll just tell you where it is and how many characters you have to copy. So that's what these arrows symbolize. Of course, if you encode this in bits, you'd have to say for this arrow, where does it point to? Where does it start? And then also, how big is this box? It's nicely drawn in this visual format, but of course, you would have to specify that for computer memory. So if you follow all the pointers, we can just do this here. So if you try to follow where this box comes from, it points to that box. All right, that points to that box. So it's some like. Okay, and this is an I, some like it. And then the other box points to in the, and then this points up here, just the circle part in the middle. And this part is an O, so it's OT that's missing here, some like it in the pot. That's how it goes, right? What I like about this is also just visually for this poem, how few characters you need in total to specify it. If you wonder what peas porridge is, that's the image on the right. It's some English dish, but I didn't get a chance to try the original. Some kind of soup. And peas like this is that's an old spelling for peas, apparently. Right. Okay, back to computer science. No recipes and poems anymore for the moment. What we've seen so far is single characters, and what we find in many texts is that there's substrings that are more frequent than others, not just single characters. I just wanted to list a few more examples to make that concrete. If you have English text, there's some frequent words that just occur all the time. If you have HTML web pages, then there's certain fragments of HTML that you'll see many times. And it makes sense to somehow represent those with less space. And Lempel is trying to do that, but not by analyzing the text up front and finding frequent subwords or anything fancy like that. It's just a simple mechanism for adaptively finding these boxes and back pointers. So the idea is, as in this poem, we store repeated parts by pointing back to where they occurred before. And more concretely, what does that look like? We can either have a single character, or we can have a substring that we've seen before. And this will we'll have some very concrete examples in a second. I just wanted to list first that there's different variants. There's two bigger families named after the papers when they were introduced, Lempel 77 and Lempel 78. For this module, it's not so important to know the differences, but I wanted to give you the terms in case this appears somewhere. If you read about compression methods, people might refer to one of those two. So you know these are two variants of Lempel, and they're a slightly different variant of what I'll show you. Lempel Welch is the algorithm that was long protected by a patent, so it wasn't used in some formats. But I think it's the cleanest way to formulate the idea, or to make the idea concrete. So what does that look like? All of these Lempel algorithms are variable to fixed. Yeah, okay, I'll take that back. Not all. Lempel Welch is clean because it's a variable to fixed coding. They all have the variable part, but producing a fixed length code word is what makes Lempel Welch a bit nicer. Think of this as being a code word of 12 bits, something like that. But the 12 bits in the coded text might represent a much longer part of the source text, if that's compressible. How will we do that? We maintain a set of phrases, a dictionary, that has up to 2 to the k entries. Well, 2 to the k just because that's how many different things you can specify with k bits. And code words, the things that we store in the coded text, these are just indices in the dictionary, specifying one of those entries. We'll always start by filling the dictionaries with these single characters in the alphabet and leave the rest empty for now, and then we'll fill it as we go. Whenever we encode some bit of the text, we'll add a new code word to the text that has something to do with what we just stored. So when we encode a substring x, that's this one. When we store that one, so okay, I should maybe explain the picture a bit better. We're currently at this point. Everything to the left is already encoded. So we assume the decoder knows that. And now we try to find a next bit that we want to encode. If that is this part x, because we could find a copy of x earlier, then we store x by a reference to this previous occurrence. And afterwards, we add x and one more letter to the dictionary. So when you keep doing this, you'll make longer and longer phrases in the dictionary, all represented by a code word of the same length. That's where the compression comes from. I think that's all for this part. Let's see a concrete example that makes this maybe more explicit. Up here is a text with lots of repetition so that we see something interesting happening for this small example. I'm taking just the entire ASCII character set as the alphabet. So we would have a dictionary that's pre-filled with all the ASCII characters. I've left out all those that we don't use, but just to keep the example more realistic, all the text characters are possible. And we'll start building the coded text step by step. Okay, how does this work? First, because we have, in each step, we try to find the longest code word in the dictionary that matches a prefix of what we have to encode. So we try to find among all those, because these are all empty, it will be just a single character. We try to find the longest thing that we've seen before. And in this case, it's just a single character. So we store the code word for y over here in the output. And that's encoding y done. But remember, after each such step, we also add something new to the dictionary, namely the thing we just encoded plus the next character. That's what the picture below here reminds you of. We've just stored x. X was only y. And then we take the next character, which is O, and we add that to the next free entry in the dictionary. All right? So far, so good. Then we keep going. We have now encoded everything to the left of this. Now we find the longest thing that we've seen so far that occurs here. We only have a longer thing that's yo, and this is not yo because it starts with O. So the best thing we can find is just a single O. That's why we get the code word 79. But we have to add something new to the dictionary again. Same game as before. We take O and the next character and stick that as a new phrase into the dictionary. All right? One more time, we have the same situation. It's a single character. We haven't seen anything bigger or longer. So we take the code word that represents the exclamation mark, put that as part of our coded text, but we also have to add a new phrase to the dictionary, namely what we've had plus one more character. All right, the same thing happens another time. I'll skip that part. We find that code. We add the new thing to the dictionary, which is the character we just stored plus one more. So far, so boring. Now, for the first time, we have something more interesting happening because we've already stored this substring yo, and that's reoccurring here. Okay? And you can obviously see this here in the example, but we'll talk about how the algorithm finds it. So we take the code word for this, which we assigned earlier. That's part of the coded text. And the rest is as before. We keep adding a new thing to the dictionary, which is the two letters we encoded plus one more. So we now have a phrase of length 3 in the dictionary. All right. For u, we have nothing that starts with u so far, so we'll get a single character, but we'll add a new phrase with the next character to the dictionary. Well, the next example, again, we've seen exclamation mark space before, so we'll get a code word for that. And again, we add to the dictionary exclamation mark space and then followed by y as the next code word. All right. And here it becomes interesting. Now we found an even longer phrase. We've seen u before, so we can take the code from there to encode the entire 3 letters, and we add one more thing as the new phrase to the dictionary. I think by now it gets a bit boring, so you've probably understood the process. Well, let's finish it quickly. So r we have not seen before, so we just get a single character, and we add r space to the dictionary with the next character. Space y we've seen before, but we haven't seen space y o. We've seen that before there's an earlier occurrence of that phrase in the text, but it's not in our dictionary. That's one of the differences between Lempel Welch and some of the other variants. We don't necessarily scan through the text and find the longest thing that we've seen before. We restrict ourselves to those that are in the dictionary. And here space y is the longest. We don't have anything space yo in the dictionary, even though that did occur earlier. Okay. All right, so we encode that and add one more thing to the dictionary for future use and keep going like this. Okay, O, we haven't seen. We have seen O, but not with a Y after it. Okay, but now we put it in. And one last one. Yo, we've seen before long ago. And then we reach the end. All good so far? If you want to implement this efficiently, here's some pseudocode that describes what I've just done. So we keep the previous phrase that we just encoded, and that's the output, the coded text. We have the dictionary. Now, we use a data structure here that we haven't discussed in detail yet. So you might only understand the running time when you come back from Unit 8 to this. The next free code word we have to store. So we already have the dictionary filled with all the characters in sigma s. So the next free code word, excuse me, is that one. Then we go through the entire text. We take the next character to encode. If the dictionary contains what we've seen so far and the next character, then we grow our phrase. So we keep making the part that we store bigger. Once we have a mismatch here, so we haven't found anything longer in the dictionary before, then we take what we currently have. We take the code word for that and add that to the output. So that's just saying append in string notation. And we add the new thing to the dictionary. That's this part. We take X and new character C, and we add that to the dictionary. Then we have to increment the next free code word is one bigger, and we have to remember that we stored this before. So basically, this is all easy if you assume that we have this function contains key. If the dictionary can somehow quickly tell us, do you have a code word of that string? Do you have that string stored as a code word, as a phrase, sorry. And we'll see that tries allow to do this in essentially constant time if you keep adding one character at a time. We'll come back to that when we discuss it in Unit 8, so you can revisit this. But basically it can be implemented using a try so that when you add one more character, you can do this in constant time to check whether you can add one more character and you still have a dictionary phrase.